For our last example today, we want to look at a calorimetry problem where we actually run a chemical reaction and we use calorimetry to determine the amount of heat absorbed or released by the chemical reaction. So we're going to look at example 9.5, which deals with heat produced by an exothermic chemical reaction, which is an acid-base neutralization, where we react hydrochloric acid with sodium hydroxide to form sodium chloride and water. To help you visualize the setup for this problem a little better and see the physical picture of what's happening, I've included a video below where you can see the manipulation of the reactants that's going to lead to this chemical reaction. What this would look like in the lab is we will combine 50 mils of a 1 molar hydrochloric acid solution and 50 mils of a 1 molar sodium hydroxide solution. Both of these are aqueous solutions, so we're essentially looking at 50 mils of two clear colorless liquids, or what appear to be two clear colorless liquids. One is hydrochloric acid dissolved in water, one is sodium hydroxide dissolved in water. The initial temperatures of both solutions are the same because they're being held at room temperature, so the initial temperature of both solutions is 22.0 degrees Celsius. They're added to a coffee cup calorimeter, and a chemical reaction takes place. The chemical reaction is 1 mole of hydrochloric acid, aqueous, reacts with 1 mole of sodium hydroxide, aqueous, to make a mole of sodium chloride dissolved in water and 1 mole of liquid water. This reaction produces heat, so it's an exothermic reaction, and it raises the temperature of the water in which the chemical reaction is taking place. So in terms of defining system and surroundings, we'll consider the actual chemical reaction that's happening to be the system, and the water that is the solvent held in the calorimeter would be the surroundings. So the chemical reaction produces heat, which is released to the water, that's the surroundings, raising the temperature inside the calorimeter, and the temperature inside the calorimeter continues to climb until we reach a maximum temperature of 28.9 degrees Celsius. We want to determine the amount of heat produced by this reaction. And in the problem it says the approximate amount of heat, but the only reason it's saying approximate is because we're making a couple of simplifying assumptions about what is heat versus what is system versus what is surroundings. That doesn't change the way that we're going to approach the problem, which will be once again to determine, using the mass of the surroundings and the temperature change of the surroundings, how much heat the reaction must have produced. All right, so once again, we'll ultimately use the calorimetry equation, Q equals mc delta T, to solve the problem. And once again, because we're dealing in a calorimeter, the central idea is that the heat released by the reaction, Q reaction, is equal to the negative of the heat gained by the surroundings. So heat released by the reaction, Q reaction, is equal to negative Q solution, the heat that's going to be gained by the water. So we can write the overall statement for the heat flow as the mass of the reactants times the specific heat for the reactants times the temperature change of the reactants is equal to the negative mass of the solution times the specific heat of the solution times the temperature change for the solution. From the data given in the problem, we really only know the mass of the solution, the specific heat of the solution, and the temperature change of the solution. We don't know anything specifically about the reactants and the chemical reaction that's happening, but that's okay. Because if our calorimeter is functioning correctly, all the heat that's produced in this chemical reaction must be absorbed by the water, which is our surroundings. And so because we're considering the dilute aqueous solutions, or really the surrounding, or the water itself to be the surroundings, the specific heat for the water is once again 4.184 joules per gram degree Celsius. That's from table 9.1. We can assume, because the concentration of hydrochloric acid and the concentration of sodium hydroxide are only 1 molar, that the density of these solutions is essentially the same as the density of water. So we can say that the density of each of our solutions that we combine to start the reaction is 1.0 gram per milliliter. So if I put in 50 mils of the hydrochloric acid and I put in 50 mils of the sodium hydroxide, I'm putting in 50 grams of this solution and 50 grams of that solution. So the total mass of the solution is 100 grams. And that's what we'll actually use in our calorimetry equation. So the mass of the solution is going to be 100 grams. The specific heat of the solution is going to be 4.184 joules per gram degree Celsius. And we need to know the temperature change. As ever, delta T, the temperature change, is the final temperature of the solution minus the initial temperature. 28.9 degrees Celsius is our final temperature minus the initial temperature of 22.0 degrees Celsius would give us our delta T. So our overall heat taken up by the solution is 100 grams, the solution's mass, times the specific heat, 4.184 joules per gram degree Celsius, times the delta T, 28.9 minus 22.0 degrees Celsius. And as ever, I'm writing these with the units included. I really encourage you to do that. 100 times 4.184 times the temperature difference gives us a heat gained by the solution of 2,886.96 joules. Grams cancels with grams in the denominator of the specific heat. Degrees Celsius cancels with degrees Celsius in the temperature change. So we could rephrase that in terms of the units if we want, remembering that there are 1,000 kilojoules. Remembering that there are 1,000 joules in a kilojoule, the heat gained by the water is 2.89 kilojoules. Since it only asks for the amount of heat produced by this reaction, you could give your answer in joules if you want, or you could give it in kilojoules. Either way is fine. Now remember, the last thing to remember is that the reaction was exothermic because causing the chemical reaction caused the surrounding water to heat up, and the heat released by the reaction is equal to the negative heat gained by the solution. And so if our Q solution was positive, the Q reaction is negative. And this is an exothermic reaction, so our final answer should be a negative 2.89 kilojoules of heat released by this chemical reaction. And so what we've looked at here is an example of how we can run a chemical reaction in a calorimeter, and based on the heat absorbed or released by the chemical reaction, we can determine whether the reaction is exothermic and how much heat is released by a specific amount of the reactants combined. And this type of calorimetry experiment is going to be essential going forward because starting next time, we'll actually talk about how we can use calorimetry to determine on a per mole basis how much heat is released by a chemical reaction, or to start talking about thermochemical equations. So again, I expect that when you're looking through these examples, they may seem to flow very naturally, and I might be making a lot of snap decisions that seem to make sense at the time. What's often hard for students is that when we sit down, it becomes challenging to differentiate what's reaction and what's solution, what's system, what's surroundings. How do we decide whether we can make an assumption like the density of hydrochloric acid is the same as the density of water? These are all valid questions that you may need to ask me as you go through your example problems and your experiments, and your practice problems and your experiments in lab, but I'm going to give you a couple of examples here. In general, if you have a solution that's in water, we'll be dealing with a concentration that's going to be dilute enough, 1 molar or less, that you can assume that the density of an aqueous solution that's placed in a calorimeter has the same density as water. So for most of the chemical reactions we'll be looking at, unless the problem explicitly says otherwise, you can often assume that the specific heat of the surroundings is the specific heat for water. Also, if you're given an aqueous solution and you need to know the mass for a calorimetry problem like this, usually they're going to be dilute enough that the density is going to be the same as that of water. 1 gram per mil is an acceptable approximation of the density. If it's not, the problem will clue you in. So keep those things in mind, but if you have questions about defining system versus surroundings, please don't hesitate to get a hold of me. I'll be happy to help you out with that anytime.